There is a moment just before sleep arrives, when the day finally lets go of you, when the thoughts begin to soften, and the world outside seems to grow a little more distant, a little more quiet. This is that moment. You are welcome here, wherever you are right now, whether you are lying in a warm bed, tucked beneath heavy covers, or resting in a chair as the evening wraps around you, or perhaps sitting quietly at the end of a long day, looking for somewhere gentle to rest your mind. You are in exactly the right place. This is the gentle cosmos. And tonight, we are going to take the quietest journey imaginable. A journey without motion, without urgency, without any destination you need to reach. We are simply going to look outward, slowly, together. If you feel like leaving a note, we would love to know where in the world you are listening from and what time of day it is for you. Whether it is deep night or a quiet afternoon, whether the sky above you is clear or clouded, that small detail connects all of us, scattered across this planet, into something a little warmer. But there is no need, just rest. Tonight's journey is about scale, the scale of the universe. Now, that might sound like a large and complicated idea, and in some ways, it is. But we are going to approach it the way you approach the night sky itself, slowly, with patience, one soft step at a time. We are not going to rush through numbers and diagrams. We are not going to chase after facts. We are simply going to let the size of things settle over us, like a blanket, like the way darkness settles over a landscape at the end of a summer evening, gently, completely. The universe is immense, that much you already know, but knowing it as a fact and feeling it as something real are two quite different experiences. Tonight, we hope to offer you a little of the second one. So, if you would like to, let your body settle a little deeper into wherever you are. Let your shoulders drop. Let your breath slow. We begin, as all journeys must, at the beginning, right here, right where you are. Consider for a moment the room you are in, the walls, the ceiling, the familiar objects of your daily life, close enough to reach, reassuring in their nearness. Now let your awareness move outward through those walls, to whatever is just outside, the street, the yard, the building beyond, then further, the neighborhood, the city or town, the coastline or the plains, the region, the country. Each step outward keeps the world recognizable, still filled with people, still organized around human concerns and emotion, but the steps are adding up. And now, the whole of the earth, seen from above. Far enough above that the curvature is visible, that weather systems are visible as patterns of white against blue. Our planet becomes something you can hold in a single thought, a sphere, mostly water, wrapped in a thin layer of atmosphere so delicate that from a certain distance it looks almost transparent at the edges. The Earth is about 12,700 kilometers across. Numbers like this are hard to feel, so consider it this way. If you shrank the Earth down to the size of a billiard ball, it would actually be smoother than a billiard ball. The mountains, the ocean trenches, all of that relief would flatten into almost nothing at that scale. The surface of the Earth to a billiard ball's geometry is essentially polished. But at its actual size, the Earth is enormous. Driving around the equator without stopping would take more than 16 days at highway speed. The ocean floor, in its deepest trench, plunges nearly 11 kilometers below the surface. The atmosphere, that thin sheltering shell that holds all weather, all breath, all sound, extends only about 100 kilometers before thinning into something effectively indistinguishable from space. 100 kilometers. If the Earth were a school globe 30 centimeters across, the atmosphere would be a layer about the thickness of a coat of paint. Yet inside that coating of air, every bird that has ever flown, every cloud that has ever formed, every thunderstorm, gentle rain and still morning, all of it fits. In 1990, as the Voyager 1 spacecraft was leaving the solar system, astronomer Carl Sagan asked NASA to turn its camera back toward Earth one last time. The resulting photograph showed our planet as a single pixel of pale blue light suspended in a beam of scattered sunlight. A mote of dust in a vast, dark room. Sagan observed that every human being who had ever lived, every figure of history, every act of courage or cruelty, every love story and every war had played out on that tiny, pale, blue dot. It is not a diminishing thought, despite how it sounds. There is something in it that reorganizes the ordinary, the daily frustrations and small concerns into something that simply requires less of your attention. The planet is real, the people on it matter, and the universe contains it all without comment or judgment. Before we leave it, one more thing about Earth. Right now, as you lie still, the Earth spins on its axis. At the equator, that surface moves at roughly 1,670 kilometers per hour, faster than most aircraft. Yet you feel none of it. The rotation is so steady, so unaccelerated, that there is no sensation. And simultaneously, the entire planet travels around the Sun at about 107,000 kilometers per hour. You are on a spinning sphere, hurling through space, and the world outside your window is perfectly quiet. That stillness is genuine, and the motion is equally genuine. Both things are true at once. On a clear night, the sky above you looks flat, a dome dark and scattered with light. But this is a very old illusion. The stars do not exist at a uniform distance from us. They only appear to, because we have no way to perceive depth across distances that large. Our eyes evolved to judge distance by parallax, the subtle shift in perspective between two eyes separated by just a few centimeters. At distances beyond a few hundred meters, that mechanism stops working. Beyond a kilometer or so, our sense of depth largely disappears. A mountain range 10 kilometers away and a cloud 20 kilometers away look equivalently far. We judge by brightness, by haze, by familiarity, not by any direct perception of distance. At the distances of stars, the numbers reduce parallax to something our eyes cannot register. Proxima Centauri, the nearest star to our Sun, is about 40 trillion kilometers away. The most distant stars visible to the naked eye on a good night are several thousand light years away, and they all appear to the unaided eye as points of light on the same flat dome. When you look at the constellation Orion, that familiar winter shape of a hunter with a belt of 3 stars, you are not looking at 7 objects at the same distance. The 3 belt stars appear nearly identical in brightness and position, but Mintaka, the rightmost, is about 900 light-years from Earth. Alnilam, the center star, is closer to 2,000 light-years. Alnitak, the leftmost, sits at roughly 1,200 light-years. They are not neighbors in space. They happen to fall along a similar line of sight from where we stand. The constellation is a perspective drawing, not a physical grouping. It is the same with every constellation you have ever known. The Big Dipper, Cassiopeia, the Southern Cross. All of them are line-of-sight patterns, like the shapes we find in clouds, real patterns perceived by real eyes. but not structures that exist at a single location in space. The brightest star in the night sky, Sirius, is only about 8.6 light-years away, a near neighbor in cosmic terms. The second brightest visible star, Canopus, is roughly 310 light-years distant. They appear comparably bright from Earth because Canopus is intrinsically much more luminous, a much larger, more powerful star. Brightness, as we perceive it, is a combination of actual luminosity and distance. The night sky does not sort itself by either. It simply shows us what arrives. There is something quietly interesting in this. The sky that looks so still and arranged is actually a cross-section through enormous depth, a window, not a dome, and the light passing through it has been traveling for years, decades, centuries, all of it arriving at the same moment, from wildly different removes. The night sky, seen honestly, is less like a ceiling and more like a long corridor. The stars are not scattered across a surface. They are distributed through a volume so large that our position within it is essentially arbitrary. We are inside the galaxy, looking outward in all directions, at objects near and distant, ancient and less ancient, arranged by history and physics, not by any pattern that serves our perception. The dome is an illusion, but the light is real. Of everything we see in the sky, the moon is the only object close enough to show a face. It has geography, craters and mountains and vast flat plains the early astronomers called Maria Seas, though they contain no water and never did. It is the only place beyond Earth where human beings have stood, and it has been with us in its present form for most of Earth's history. But the moon was not always there, and understanding how it came to be tells us something about how violent the early solar system truly was. At some point during this period, a body roughly the size of Mars, sometimes called Theia, struck the young Earth. Not a glancing blow, a direct impact. The collision was large enough to vaporize much of both bodies. The outer layers of the Earth and much of the impactor were blasted outward into space as an enormous ring of molten rock and vapor. Over thousands of years, that material gathered under its own gravity. It cooled, it solidified, and what remained, orbiting the damaged, reforming Earth, was the moon. This is the leading explanation for the moon's formation, supported by the composition of lunar rocks returned by the Apollo missions. The moon and Earth share a chemical signature. Their isotopic fingerprints are unusually similar, more so than we generally find between bodies thought to have formed independently. They were made in large part from the same material, a violent sharing. In the early years after its formation, the moon was much closer to Earth, perhaps a quarter of its current distance. From Earth's surface in that era, the moon would have appeared enormous, a massive presence, distorted and slow-moving across the sky. The tides it raised would have been extreme. The ocean, if it existed yet, would have been pulled into walls of water many times higher than anything we experience today. The moon has been moving away ever since, not quickly, about 3.8 centimeters per year, roughly the rate at which fingernails grow. We know this with precision because the Apollo missions left retroreflectors on the lunar surface, small arrays of mirrors, and we bounce lasers off them to measure the distance exactly. The moon is measurably, verifiably receding. Given enough time, billions of years, it will eventually settle into a more distant, stable orbit, and the tidal forces that have shaped Earth's geology and biology for billions of years will gradually weaken. The moon also does something that tends to go unappreciated. It stabilizes Earth's axial tilt, Earth is tilted on its axis at about 23.5 degrees, a tilt responsible for our seasons, for the variation in daylight, for the way life has adapted to the rhythm of the year. Without the moon's gravitational steadying influence, that tilt would drift chaotically over long timescales, ranging perhaps from nearly 0 to more than 80 degrees. The climate implications would be severe. The stability that life on Earth has enjoyed for hundreds of millions of years is, in part, a gift from the moon. And all of this from an impact of a scale that should, by most intuitions, have left nothing behind worth keeping. The moon sits tonight where it always sits, at its current phase, at its current distance, rising and setting with the rotation of the Earth. It has been doing this for longer than there were eyes to see it, steadily, quietly, keeping pace. The word solar system suggests a kind of togetherness, a family, a system with components that belong to each other. And in a gravitational sense, that is true. Every planet, moon, asteroid, and comet is bound to the Sun, orbiting it on timescales from months to millions of years. But if you were to visit the solar system, the overwhelming experience would not be togetherness. It would be emptiness. The solar system is almost entirely empty space. The Sun accounts for about 99.86% of all the mass in the entire system. The planets and everything else, Jupiter, Saturn, all the moons, the asteroid belt, the Kuiper belt, share the remaining 0.14% between them, and even that material is spread across an enormous volume of space. The astronomical unit, 1 AU, is the distance from Earth to the Sun, about 150 million kilometers. It is our standard measuring stick for the inner solar system. Mercury orbits at about 0.4 AU, Venus at 0.7, Mars at 1.5. The asteroid belt stretches from about 2.2 to 3.2 astronomical units. Jupiter sits at 5.2, Saturn at 9.5, Uranus at 19, Neptune at 30. Those numbers scale in a way that is genuinely difficult to absorb. So consider this. If you placed a standard soccer ball at one end of a football field to represent the Sun, Earth, at that same scale, would be the size of a small peppercorn, and it would sit roughly 30 meters away from the soccer ball. Jupiter, at that scale, would be a marble, about 150 meters from the ball, and Neptune, a small grape, would sit nearly 900 meters away, almost a kilometer, between a soccer ball and a grape, 900 meters of empty space. The gaps between the planets are not merely large, they are larger in proportion to the objects within them than almost any gap we have experience of on Earth. Standing on the surface of Mars and looking toward Jupiter, Jupiter would not be visible to the naked eye as a disk. It would be a bright point of light. The planets do not loom over each other. They are simply somewhere in the dark. Moving outward from Neptune, the solar system does not simply end, it thins. The Kuiper belt extends from about 30 to 50 astronomical units, a wide ring of icy objects, including Pluto and hundreds of smaller bodies, circling slowly in the outer dark. Beyond that, a region called the scattered disk, a more distant and dynamically stirred population of icy objects, some of which occasionally fall inward toward the Sun and become long-period comets. And surrounding all of it, extending outward to perhaps 100,000 astronomical units from the Sun, lies the Oort cloud, a theoretical shell inferred from the behavior of comets not yet directly observed, composed of billions of icy bodies held very loosely by the Sun's gravity. At 100,000 astronomical units, the Sun is just a bright star. Its gravity is barely enough to hold them. The sun's light takes 8 minutes to reach Earth, about 43 minutes to reach Jupiter, and more than 14 hours to reach the outer boundary of the Kuiper belt. To reach the inner edge of the Oort cloud would take light nearly a month and a half. To reach its outer edge, more than a year. The Voyager 1 spacecraft, launched in 1977, now traveling at about 61,000 kilometers per hour, only crossed the inner edge of the heliosphere, the bubble of solar wind that defines the sun's immediate influence, in 2012. 35 years of travel to cross the first layer of the outer solar system. Even Voyager's modest instruments, the sum of human engineering launched almost 50 years ago, are still transmitting, still sending data back across that immense distance, taking more than 22 hours for each signal to arrive at Earth. One spacecraft, moving through mostly nothing, in a system that is mostly nothing. And the solar system is one of hundreds of billions in this galaxy alone. Almost everything we know about the universe beyond our solar system, we learned from light, not from samples, not from instruments we sent there, not from any form of contact, just light. This is worth sitting with because it shapes everything that follows. When we describe the temperature of a star, its chemical composition, how fast it is moving, how old it is, whether it has planets, nearly all of that information was extracted from photons, particles of light that traveled immense distances and arrived at a detector where we read them. The primary tool for doing this is spectroscopy. When light passes through a prism, or through any dispersing element, it spreads into its component wavelengths. A rainbow is the most familiar version of this, but a rainbow carries information. When astronomers spread starlight into its spectrum, they find it is not a continuous band of color. It is interrupted by dark lines. These lines appear at very specific wavelengths, precise locations in the spectrum, and they correspond to the fingerprints of chemical elements. Every element absorbs and emits light at characteristic wavelengths that are fixed by the laws of physics. Hydrogen has its lines, helium has its lines, calcium, iron, sodium, each element leaves a distinct pattern. From the spectrum, astronomers can also determine temperature. Hotter objects emit more of their light at shorter wavelengths, toward the blue end of the spectrum. Cooler objects emit more at longer wavelengths, toward the red. A star's color is a direct indicator of its surface temperature. Blue-white stars are extremely hot. Orange and red stars are cooler. Our sun is a middle-of-the-road, yellow-white, with a surface temperature of about 5,500 degrees Celsius. And, from the motion of those spectral lines, whether they are shifted toward the red or the blue end of the spectrum, relative to where we expect them, we can determine whether a star is moving toward us or away. This is the Doppler effect applied to light. A star moving away has its light stretched slightly toward longer wavelengths. A star approaching has its light compressed toward shorter wavelengths. The shift is measurable, and it tells us not only about individual stars, but about the expansion of the universe itself. When Hubble observed in the 1920s that distant galaxies were almost universally red-shifted, it was the first evidence that the universe was growing larger. Astronomers also use the geometry of light to measure distance. Nearby stars show a measurable shift in apparent position as Earth moves around the Sun, a technique called parallax. The shift is tiny even for nearby stars, and for the closest stellar neighbors requires very precise instruments to detect. but it provides a direct geometry-based measurement of distance, no assumptions required. For distances too vast for parallax, other methods exist. Certain stars pulsate at rates directly related to their intrinsic luminosity. By measuring how bright they appear and comparing it to how bright they actually are, astronomers calculate the distance. Step by step, each method calibrates the next, a ladder of techniques that carries our measurements from the nearest stars to the most distant galaxies, all of it built on light, on the patience to collect it, and on the insight that the universe speaks in a language physics can translate. Stars are not eternal. They have a beginning, and the beginning is cold. Scattered through the Milky Way, between the stars we can see, are immense clouds of gas and dust, mostly hydrogen, some helium, traces of heavier elements, dust grains made of carbon and silicates, molecules of water and carbon dioxide frozen onto those grains. These clouds are called molecular clouds, and they are among the largest structures in the galaxy. Some span hundreds of light years. Some contain enough material to form millions of stars. For long periods, a molecular cloud simply drifts. It has internal pressure that keeps it from collapsing under its own gravity. Cold gas pushes outward as heat presses back. For millions of years, sometimes tens of millions, nothing dramatic happens. But molecular clouds are not isolated. The galaxy is full of events that disturb them. A nearby supernova, the explosive death of a massive star, sends a shock wave through the surrounding gas. The spiral arms of the galaxy, as the cloud drifts through them, create density waves that compress the gas. When a region of a molecular cloud is compressed enough, gravity begins to win. A small region starts to contract. As it contracts, it warms. As it warms, it radiates energy. This object, a collapsing, warming ball of gas that has not yet ignited nuclear fusion, is called a protostar. The protostar continues to collapse, growing hotter at its center. It may begin to spin faster as it shrinks, flattening into a disk of gas and dust around it, a protoplanetary disk. Planets may form in that disk over millions of years, accreting from the same material that surrounded the growing star. At the core of the protostar, temperatures climb into the tens of millions of degrees, and at some point, a moment that has no official name but deserves one. The temperature and pressure become sufficient for hydrogen nuclei to fuse. Two hydrogen nuclei combine to form helium, releasing energy. Then again and again, the process ignites, and the protostar becomes a star. The pressure of that outward flowing energy, the pressure of light and heat generated by fusion, now pushes back against the inward pull of gravity. A balance is struck. The star settles. It begins to shine steadily. A star like our Sun takes roughly 50 million years to reach this point from the initial collapse. You can see this process happening right now. The constellation Orion, visible from most of the world in winter, contains the Orion Nebula, a smudge of light just below Orion's belt, visible to the naked eye under dark skies. The Orion Nebula is an active stellar nursery. Within it, hundreds of young stars have formed in the past few million years. Some are still surrounded by their protoplanetary disks. Some may already have planets. When the Hubble Space Telescope imaged the Orion Nebula in detail, it revealed thousands of young stellar objects, protostars at various stages of development. embedded in swirling columns of gas and dust. The light from the Orion Nebula left about 1300 years ago. In that light is the ongoing story of stellar birth, new suns switching on in the dark, the galaxy continuously replenishing itself. A star, at its simplest, is a negotiation, two forces perpetually opposed. Gravity pulls inward, always pulling, never stopping, trying to compress the star into an ever smaller point, and from the core, energy flows outward. Heat, light, radiation generated by the fusion of hydrogen into helium pushing back. As long as the outward pressure matches the inward pull, the star remains stable. It holds its shape. It shines. This stable period is called the main sequence, and for a star like our Sun, it lasts about 10 billion years. Our Sun is roughly 4.6 billion years old. It is, by stellar standards, middle-aged. The duration of this stable period is not the same for all stars, and this is where stellar physics becomes genuinely interesting. More massive stars burn hotter and faster. A star 10 times the mass of the Sun burns through its hydrogen fuel not in 10 billion years, but in tens of millions. It lives fast in the truest sense. It produces far more energy per unit of time. It blazes blue-white and brilliant, but it exhausts itself quickly. Smaller stars, like red dwarfs, which make up the majority of stars in the galaxy, burn so slowly that some of them may outlast the current age of the universe many times over. They are dim, cool, patient. They will still be burning when stars like our Sun have long since ended. What happens when a star's hydrogen supply runs low depends almost entirely on how massive it is. For stars like the Sun, middle-mass stars, the story goes like this. As hydrogen in the core is depleted, the balance shifts. The core contracts under gravity, heating further. This extra heat causes the outer layers of the star to expand enormously. The star swells over millions of years into a red giant. It becomes larger and cooler at its surface, even as its core grows hotter and more compressed. At its peak, a red giant may expand to 100 times the Sun's current diameter. If our Sun reaches that size in about 5 billion years, it will engulf Mercury, likely Venus, and possibly Earth. Eventually, the red giant exhausts its remaining fuel. The outer layers are gently expelled, not in an explosion, but in a slow, beautiful exhalation, a shell of gas expanding outward into the surrounding space. Lit by the star's remaining core, these expanding shells glow in colors determined by their composition: greens, blues, reds. Astronomers call them planetary nebulas, though they have nothing to do with planets. The name is a historical accident. Early observers thought they resembled the disks of planets through small telescopes. What remains at the center is a white dwarf, a dense, glowing remnant, roughly Earth-sized, but containing most of the original star's mass. No more fusion, no more fuel, just a slow release of stored heat, cooling over billions of years. The eventual end state, if left undisturbed long enough, is a cold, dark remnant called a black dwarf. Though the universe is not old enough for any white dwarf to have cooled that far yet. For much more massive stars, the ending is different and more dramatic. When a massive star exhausts its fuel, gravity wins too quickly and too completely. The core collapses in less than a second. What follows is one of the most energetic events in the known universe, a supernova. The collapsing core rebounds, sending a shock wave outward through the star's outer layers. Those layers are blown outward into space at a significant fraction of the speed of light. For a brief period, a single supernova can outshine an entire galaxy. For the most massive stellar cores, not even neutron degeneracy can halt the collapse. Gravity wins completely. What remains is a black hole, a region of space from which nothing, no matter, no light, can escape. But here is what often gets overlooked in discussions of stellar death. The explosion of a massive star is not just an ending. It is a seeding. The shock wave of a supernova compresses surrounding molecular clouds, sometimes triggering the birth of new stars. And the material blown outward, the heavier elements forged in the star's core over millions of years, carbon, oxygen, iron, calcium, silicon, all of it disperses into the surrounding space, where it may, in time, become part of a new molecular cloud, part of a new protoplanetary disk, part of a new world. The calcium in your bones was forged in a star, not our sun. It hasn't had the time or conditions to produce calcium. An older star, long dead, whose explosion seeded the cloud that eventually became our solar system. Stars end so that other things can begin. Between the stars, space is not empty. It only appears empty. The material that fills interstellar space, thinly, incomprehensibly thinly, is called the interstellar medium. It is a mixture of gas and dust threaded through with magnetic fields, bathed in radiation from all directions and crossed constantly by high-energy particles. The gas is mostly hydrogen. In the coldest, densest regions, hydrogen molecules cluster together in clouds. The molecular clouds that we have already seen can collapse into stars. In warmer regions, hydrogen exists as individual atoms. In the hottest regions, near young hot stars, or in the aftermath of supernovas, hydrogen is ionized. Its electrons stripped away, leaving a plasma of bare protons and free electrons. These glowing regions of ionized hydrogen are some of the most visually striking objects in the galaxy. The Orion Nebula, the Lagoon Nebula, the Eagle Nebula, home of the famous Pillars of Creation. All of them are regions where hot young stars have ionized the surrounding gas, making it glow. The dust component of the interstellar medium consists of grains, tiny particles, typically a fraction of a micrometer across, carbon compounds, silicates, ices. The dust is why we cannot see the center of the Milky Way in ordinary light. Between us and the galactic core lie thousands of light years of dusty interstellar medium. Visible light cannot pass through it cleanly. Infrared light, longer wavelengths can. And when astronomers observe the galactic center in infrared, the dust becomes transparent, and the dense, busy, remarkable center of our galaxy comes into view. Threading through all of this gas and dust are magnetic fields. Galactic magnetic fields are weak by any everyday standard, billions of times weaker than a refrigerator magnet, but they extend across enormous distances. They shape the behavior of charged particles moving through the interstellar medium. They influence the structure of molecular clouds. They contribute to the complex dynamics of the galaxy in ways that are still being actively studied. And then there are cosmic rays. Not rays in the traditional sense, not photons, not light, but individual particles. mostly protons, accelerated to extraordinary energies by supernova shockwaves and other violent events. They travel through the galaxy at close to the speed of light. Some of them, arriving at Earth's atmosphere, generate cascades of secondary particles that rain down to the surface. Cosmic ray detectors at research stations in Antarctica, in remote mountain observatories, record these arrivals constantly. The most energetic cosmic rays carry kinetic energies equivalent to a well-thrown baseball in a single proton. The interstellar medium is not a backdrop. It is an environment, one that connects the history of dead stars to the birth of new ones, that transports energy and material across vast distances, that makes the galaxy a dynamic, circulating system rather than a collection of isolated objects. Between the stars, there is something, very thin, very spread out, but real, and part of the same story everything else belongs to. We know the Milky Way is a barred spiral galaxy. We know it spans roughly 100,000 light-years across. We know it contains somewhere between 100 billion and 400 billion stars. We know the Sun sits about 26,000 light-years from the center, in a quieter outer region called the Orion Arm. But here is something worth pausing on. We have never seen the Milky Way from the outside. No spacecraft has traveled far enough. No telescope exists with the power to see our galaxy from a distance. Everything we know about the structure of the Milky Way, its spiral arms, its central bar, the distribution of its stars and gas, was figured out from the inside. This is like trying to draw an accurate map of a city you have never left, using only what you can observe from one fixed location. It takes ingenuity, and it took decades of careful observation. The basic shape, that we live in a disk, was understood first by counting stars. In the 18th century, William Herschel systematically counted the number of stars visible in different directions and concluded that the galaxy was a flattened disk, with the solar system somewhere near the center. He was right about the disk shape. He was wrong about our position. The solar system is nowhere near the center. We just happen to live in a region where the dust is dense enough that we cannot see very far toward the core invisible light, making the galaxy appear roughly symmetric from our location. It was not until the 20th century, with radio astronomy and infrared observations that could penetrate the interstellar dust, that astronomers began to map the galaxy accurately. Radio waves emitted by hydrogen gas are not absorbed by dust, they pass through it freely. By mapping the distribution of hydrogen in the galaxy using radio telescopes, astronomers could begin to trace the spiral arm structure. The galactic center itself is a remarkably dense and active region. At its very heart sits Sagittarius A star, a supermassive black hole with a mass of about 4 million suns. We know it is there because we can track the motions of stars very close to the galactic center. Over decades of observation, astronomers have watched individual stars orbit the center at extraordinary speeds. One of them, known as S2, completes a full orbit in just 16 years. From those orbital velocities and the geometry of the orbits, the mass at the center can be calculated precisely. 4 million solar masses contained in a region smaller than our solar system. Most of the time, Sagittarius A star is quiet, not actively consuming. But occasionally, when a cloud of gas drifts too close or a small object wanders within its gravitational reach, there is a flare, a brief brightening across X-ray and radio wavelengths, then quiet again. Our galaxy also has a halo, a roughly spherical distribution of older stars and globular clusters extending above and below the disk. The halo contains some of the oldest stars in the galaxy, formed billions of years before the disk settled into its current shape. These ancient stars carry a chemical fingerprint of the early universe, low in heavy elements which had not yet been produced by the first generations of supernovas. And wrapping around all of this, extending far beyond even the halo, is dark matter, an invisible halo of material we cannot directly detect, inferred from its gravitational effects on the stars and gas we can see. The Milky Way's dark matter halo is far larger than the visible disk, extending perhaps 100 times further out. Most of the galaxy's mass, by current estimates, is in this unseen form. We live at the edge of a city we have never fully seen, but we have learned to read its structure from the inside. In the frequencies of light the dust cannot block, in the motions of stars tracing the gravity of what lies at the center, in the chemical compositions that record the history of stellar generations we were not present for. It is indirect knowledge, but it is knowledge. For most of human history, the question of whether other stars had planets was unanswerable. We could speculate, but we had no way to know. That changed in 1992 when the first confirmed exoplanets were detected, and more definitively in 1995 when the first planet orbiting a Sun-like star was confirmed. Since then, the count has grown from a handful to thousands. As of recent catalogues, astronomers have confirmed over 5,000 exoplanets, with thousands more candidates awaiting verification. Other worlds are not theoretical, they are a census. The reason we couldn't find them earlier is purely a matter of scale. Even the largest planets are tiny compared to their parent stars, and they shine only in reflected light. At interstellar distances, directly imaging a planet is like trying to see a firefly hovering next to a lighthouse from several hundred kilometers away. So astronomers found indirect methods. The most productive has been the transit method. If a planet's orbital plane happens to be aligned with our line of sight, it will periodically pass in front of its star. When it does, it blocks a tiny fraction of the star's light, typically less than 1%. This dimming is regular, predictable, and detectable with precise enough instruments. The Kepler Space Telescope, launched in 2009 and retired in 2018, stared at a single patch of sky continuously for years, monitoring the brightness of over 150,000 stars. It found more than 2,600 confirmed planets. A complementary technique, the radial velocity method, detects the slight gravitational tug a planet exerts on its star. As a planet orbits, it causes the star to wobble slightly, moving toward and away from Earth in a regular pattern. This motion shifts the star's spectral lines, the same Doppler effect that tells us the universe is expanding. By measuring the wobble, astronomers can determine the planet's mass and orbital period. What these methods have revealed is a galaxy full of planetary systems. Not all of them like ours. Many have hot Jupiters, massive gas planets orbiting so close to their stars that their years are measured in days. Many have super-Earths, planets larger than Earth but smaller than Neptune, a size that doesn't exist in our solar system but appears to be common across the galaxy. Many have planets in eccentric orbits or binary star systems where two suns share a sky. The variety reaches further than anyone anticipated. There are lava worlds, rocky planets orbiting so close to their stars that their surfaces remain permanently molten. There are water worlds where deep oceans may cover everything with no exposed land at all. There are puffy gas giants, enormous planets with densities lighter than balsa wood, their outer layers bloated by proximity to their star's heat. The concept of the habitable zone is central to the search for life. It describes the range of distances from a star at which liquid water could theoretically exist on a planet's surface. Not too hot, not too cold. Many confirmed exoplanets sit within their star's habitable zone. Some are rocky, as best we can tell. Some are close to Earth-sized. The TRAPPIST-1 system, discovered in 2017, contains 7 Earth-sized planets orbiting a small red dwarf star about 40 light-years away. 3 of those planets sit within the star's habitable zone. 7 worlds, each potentially with a surface 40 light-years, close in the context of the galaxy. We do not know if any of these planets has life. The question is not answerable with current technology, but the phrasing of the question has changed fundamentally. It is no longer, do planets around other stars exist? That is settled. The question now is, what kinds of worlds are most common? What conditions do they have, and what does that imply? The answers are still arriving, one planet at a time, from stars that have not noticed us at all. The Milky Way is one galaxy. There are, within the observable universe, an estimated 2 trillion more. They are not all alike. A century of observation has revealed that galaxies come in shapes that each carry their own history. That the form a galaxy takes is an account of what happened to it over billions of years. Some of them look, from a distance, a great deal like the Milky Way. They have bright cores and arms of stars and glowing gas curling outward, the kind of structure visible in long exposure photographs taken by amateur astronomers with modest equipment from dark sky sites. These spiral galaxies are still actively forming new stars. Their arms are not rigid features but regions of density, like the compression that builds at a motorway merge, through which stars and gas continuously pass, new generations of stars igniting as the material clusters and condenses. Spirals tend to be galaxies that have been left, in relative terms, to themselves. Their structure has not been heavily disrupted by close encounters. Other galaxies have no arms at all, rounder, smoother, sometimes elongated into shapes that look like softened cylinders. These are elliptical galaxies, and they tell a different story. Their star-forming days are largely behind them. What they contain, mostly, are older stars, populations that formed and aged before the galaxy's cold gas was used up or expelled. They are quieter systems, their light steady and warm, rather than punctuated by the blue-white brilliance of young, newly formed suns. In many cases, elliptical galaxies carry the evidence of earlier violence. When 2 large spiral galaxies merge, a process taking hundreds of millions of years, their stars passing through each other's space, gravity pulling both into new shapes. What eventually settles is often an elliptical, something calmer than either original, shaped by the long aftermath of collision. The Milky Way and Andromeda, in their eventual merger billions of years from now, are expected to produce something like this. And then there are the irregular galaxies, those that fit neither category. often the product of gravitational encounters that were too close or mergers still in progress. They have been pulled into shapes without the geometry of a spiral or the symmetry of an ellipse. The Magellanic Clouds, those two faint patches visible from the southern hemisphere, are examples. Both are companions to the Milky Way, both being slowly drawn inward by our galaxy's gravity, their stars and gas stretching out into long trailing streams. In a few billion years they will likely cease to exist as separate systems entirely. Some galaxies announce themselves through something other than their stars. At the heart of these galaxies, a supermassive black hole is actively accreting material, drawing in gas and dust from the surrounding region, releasing enormous amounts of energy in the process. Some of these, called quasars, were among the most luminous objects in the early universe, so bright that they outshine their entire galaxy by factors of hundreds. Quasars are not common in the local universe. They were far more common in the past, when the universe was younger and denser and the black holes at galaxy centers had more material to consume. Looking at quasars is, again, looking backward in time. On the very largest scales, galaxies do not float freely through space. They gather loosely at first, dozens of galaxies bound to one another across millions of light years, moving together through the larger dark. These galaxy groups and clusters are themselves part of even larger concentrations, superclusters spanning hundreds of millions of light years, and connecting the superclusters to each other, threading through the space between them, are vast filaments of galaxy groups, creating a structure that astronomers call the cosmic web. The voids between the filaments, regions where almost nothing lives, can stretch hundreds of millions of light years across. The filaments themselves are sometimes described as the largest structures in the observable universe. They formed from tiny quantum fluctuations in the density of the early universe, amplified over billions of years by gravity. What were once infinitesimally small variations in density became, over time, the architecture of everything. The web of matter and light that constitutes the observable universe in its current form, all of it structured, all of it connected, all of it the slow result of physics doing exactly what physics does for a very long time. There is something unusual about looking at the night sky. Not strange, just unusual. Something that takes a moment to sit with properly. When you look at a star, you are not seeing it as it is now. You are seeing it as it was. Light travels at approximately 300,000 kilometers per second. This is genuinely fast. Fast enough to circle the Earth 7 times in a single second. But space is large enough that even this speed requires time to cross it. The light from the moon takes 1.3 seconds to reach us. From the sun, about 8 minutes. From Jupiter, depending on its position, somewhere between 35 and 52 minutes. From Neptune, over 4 hours. For stars, the numbers grow quickly. The nearest star beyond our sun is about 4.2 light-years away. The light reaching us from it tonight left 4.2 years ago. The star visible in your sky as the bright point called Sirius, the brightest star in the night sky, shows you Sirius as it was 8.6 years ago. A star 500 light-years away is showing you itself as it existed in the early 1500s. A star 1,000 light-years distant is showing you the year 1025. The stars in our night sky are not a snapshot of the present. They are a mosaic of different pasts, light from different eras arriving simultaneously, creating the impression of a single, unified sky. For objects beyond our galaxy, this temporal depth grows dramatic. The Andromeda Galaxy, the faint smudge visible in very dark skies, is 2.5 million light-years away. What you are seeing is Andromeda as it existed 2.5 million years ago. In the time that light was traveling, the earliest members of our genus had only recently appeared. Stone tools existed in their simplest form. Fire, language, and any capacity to look up and wonder at the night sky were still more than 1 million years away. The most distant galaxies we have detected in deep-field photographs, objects at the very edge of our observational reach, are showing us themselves as they existed over 13 billion years ago. Less than 1 billion years after the Big Bang, very young galaxies, irregular and small and furiously forming stars. Nothing like the large organized spirals and ellipticals of the local universe, because the local universe has had 13 more billion years to develop. Among the sciences, astronomy has perhaps the most immediate access to the past. A geologist must infer ancient conditions from the record preserved in rock. A historian reads accounts written after the fact, but an astronomer can point a telescope and see the light is there, still arriving. Still carrying information about what things looked like billions of years ago. The deepest look backward available to us is the cosmic microwave background, light released approximately 380,000 years after the Big Bang. Before this point, the universe was so hot and dense that it was opaque. Photons couldn't travel without being immediately absorbed and re-emitted. The universe glowed but was not transparent. As the universe expanded and cooled to about 3,000 degrees Kelvin, electrons combined with protons to form neutral hydrogen atoms. The universe became suddenly transparent, and the light that had been trapped in the hot plasma was finally free to travel. It has been traveling ever since. What began as visible light, photons of red and orange, has been stretched by 13.8 billion years of cosmic expansion, stretched all the way down into microwave frequencies. It is no longer visible to the eye, but it fills the sky in every direction. It is the oldest light we can detect, and it carries, embedded in its tiny temperature fluctuations, variations of roughly 100,000th of a degree, the seeds of every structure that would form afterward. The faint pattern in the cosmic microwave background is the blueprint of the universe's large-scale structure. Over hundreds of millions of years, galaxies grew in the very regions those ancient fluctuations had seeded. We are reading a 13.8 billion-year-old map, and it still describes the world we live in. The universe is approximately 13.8 billion years old. Light has been traveling through it since its earliest moments, so you might expect the farthest we could see to be 13.8 billion light-years in any direction. But that is not quite right. The universe has been expanding since the Big Bang, not expanding into something else. The universe does not have an edge that is pushing into empty space beyond it. Rather, the space itself is stretching. Every region of space is moving away from every other region, not because anything is passing through space, but because the space between things are growing. But that is not quite right. The galaxies at the edge of what we can observe were much closer to us when their light began its journey. But in the time that light was traveling, 13.8 billion years, the universe expanded significantly. The regions that emitted that ancient light are now much further away than the distance the light itself traveled. This means the observable universe, the sphere of space from which light has had time to reach us, has a radius of about 46 billion light-years, a diameter of about 93 billion light-years, not 27.6 billion as a simpler calculation might suggest. The observable universe is everything within that sphere. It is defined by our position, by the age of the universe, and by the speed of light. Every observer, anywhere in the universe, has their own observable sphere centered on themselves. Different observers see different, though overlapping, portions of the whole. In 1995, the Hubble Space Telescope was aimed at a tiny region of sky near the constellation Ursa Major, a patch chosen specifically because it appeared to contain nothing of interest. The telescope stared at it for 10 consecutive days. What it found was approximately 3,000 galaxies. This image, the Hubble Deep Field, remains one of the most consequential photographs in the history of science, not because of what it found, but because of what it implied. If every tiny, empty-looking patch of sky contains thousands of galaxies, the universe is full in every direction, not sparse, full. Subsequent observations, the Hubble Ultra Deep Field, the Extreme Deep Field, pushed further still. The Extreme Deep Field contains roughly 5,500 galaxies in an area about 1/32 millionth of the total sky. Scale that fraction across the complete celestial sphere, and the numbers become numbers that language does not handle well. The full universe, what actually exists beyond the boundary of what light has reached us from, may be far larger than the observable portion. Some cosmological models suggest it extends many times larger than the 93 billion light-year sphere. Some models suggest it may be infinite. If the universe is infinite, then there is no center, no edge. Every location is, in a sense, the middle of an infinite expanse. Every observer surrounded by an equal depth of universe in all directions. The observable universe is not a wall. It is a horizon. The light beyond it is traveling. It simply has not arrived yet. The standard cosmological model is one of the most successful scientific frameworks ever constructed. It describes the origin, the structure, and the large-scale evolution of the universe. It makes predictions that have been tested against observation with extraordinary precision. The cosmic microwave background, the distribution of galaxies across the sky, the abundance of hydrogen and helium in the universe, all of it matches the model's predictions to a degree that would have seemed implausible a century ago. And yet, the model depends on two components that we cannot directly detect, do not fully understand, and have not yet identified at a fundamental level. The first is dark matter. The evidence for dark matter comes from multiple independent directions. Galaxies rotate in a way that cannot be explained by the mass of the visible stars and gas alone. The outer regions of galaxies rotate too fast. If only the visible mass were present, the outer stars would fly apart. Something is providing additional gravitational force. Gravitational lensing, the bending of light from distant objects by the gravity of closer ones, reveals mass in regions where no visible matter exists. The large-scale structure of the universe, the way galaxies cluster, cannot be reproduced in computer simulations without including a dark matter component. The converging lines of evidence point strongly toward the same conclusion. Most of the gravitational mass in the universe appears to be in a form we cannot yet see. Dark matter makes up about 27% of the universe's total energy content. Ordinary matter, everything made of atoms, everything we have ever observed directly, accounts for roughly 5%. The other 68% is something we call dark energy. In 1998, two independent teams of astronomers were measuring the brightness of distant supernovas to track the expansion of the universe. They expected to find that the expansion was slowing down, that gravity, acting over cosmological scales, would be gradually decelerating the outward motion that began at the Big Bang. What they found was the opposite. The expansion is accelerating. Something is causing space to expand at an increasing rate. We named this something dark energy. What dark energy actually is remains unknown. The simplest interpretation, that it is some intrinsic property of space itself, fits the available data. But when theorists attempt to calculate what that property should be, the numbers do not agree with what we observe. The gap is very large. It is one of the more significant unresolved tensions in modern physics. So, 5% ordinary matter, 27% dark matter, 68% dark energy. The universe, as we can currently measure it, is 95% something we do not understand at a fundamental level. This is not presented as a source of anxiety. It is the state of knowledge at this particular moment in history. Every generation of scientists inherits a map with blank spaces. The blank spaces are not failures. They are the places that made future careers possible. They are where the next generation will build the next model. Other deep questions wait at the edge. What happened before the Big Bang? Or whether that question is even meaningful, given that time itself may have originated at that moment. Whether the constants of physics, the strength of gravity, the mass of the electron, are fixed, or whether they vary across regions of a larger universe we cannot observe, whether our universe is one of many. This last possibility, sometimes called the multiverse, arises as a consequence of certain theoretical frameworks, particularly some versions of inflationary cosmology. It is genuinely contested. Many physicists find the idea uncomfortable, not because it is unintelligent, but because a hypothesis that is permanently beyond observation sits in difficult philosophical territory. Science has generally depended on the ability to test ideas against evidence. A universe that cannot be reached, observed, or measured in any way places itself outside that framework, which means we may never be able to say, in any rigorous sense, whether it exists. Others argue that if the mathematics of well-tested theories leads to the prediction of other universes, dismissing the prediction requires a reason. The debate is real, the question is genuinely open, and it may remain that way. The frontier of cosmology today is a strange and honest place. We have extraordinary tools, extraordinary data, and a model that works remarkably well. And we know clearly that the model is incomplete, that the map has blank spaces, and that the blank spaces are the most interesting places on it. We have been out a long way tonight, through the layers of the solar system, into the silence between the stars, through the structure of the galaxy, past the galaxies beyond it, to the edge of what light has shown us, and back through time to the oldest signal the universe has ever produced. It is a long way to come back from, so we come back slowly. The cosmic web of filaments and voids, the supercluster, the local group. The Milky Way, slowly turning in the dark, its spiral arms trailing through a galaxy of hundreds of billions of stars. Our quiet spiral arm. Our sun, one star burning steadily 8 light minutes away. The solar system arranging itself in the dark around that star. The 8 planets in their orbits, each one a different kind of world. Earth, small, blue, water-covered, wrapped in its coat of air. The continent you are on, the country, the city or the countryside, the building, the room, this room, you, right here. Body still, breath slow. You are made of the oldest material in the universe. The hydrogen in your body formed in the first minutes of time. The heavier elements, the ones that make cells and bones and blood, were forged inside stars. Stars that lived and died before our sun existed. Their endings seeded the cloud that became our solar system. Their material became, eventually, the ground, the water, and you. This is not a metaphor. It is the literal account of where the atoms in your body came from. You are as old as the universe in your most basic components. You are as local as this room in your most immediate self. Both are true. The universe does not announce this. It does not ask to be acknowledged. It does not require understanding. It simply continues, expanding at an accelerating rate, forming new stars in molecular clouds we have not yet catalogued, spinning galaxies through the long arcs of their orbits. And somewhere in all of that, on a small rocky planet around an ordinary star, something organized itself into a form that could notice, that could look outward and ask how far it goes, that could spend a quiet night traveling from here to the edge of everything and back again, without moving. That is an unusual thing to be. There is nothing left to do with it tonight, but let it rest. The questions do not need answering before morning. The distances do not need measuring. The light is still arriving, and the telescopes are still open, and none of it is going anywhere. Let your thoughts move where they want to. Let the darkness be what it is. Not empty, not threatening, just the ordinary companion of every sleeping creature on this planet. You are on a world that has been moving through that darkness for 4.5 billion years. It knows the way. The stars are where they have always been. The universe is doing what it always does, and you are exactly where you should be. Because now is time for rest.